Hello folks, my name is Mark Wilson and I'm the founder of AccuModel, where we inspire confidence in hydraulic modeling. This video is a continuation of 3 other videos that precede it on Eppanet hydraulics. And this is sort of the culmination of these videos where we're actually going to try to show how Eppanet solves the equations of hydraulics for pipes and nodes to come to a solution of nodal head and pipe flow. Okay, just on screen here I've got a little snippet from Eppanet 2 User's Guide Appendix D, where it describes the method used in Eppanet to solve the flow continuity and head loss equations that characterize the hydraulic state of the pipe network at a given point in time can be termed a hybrid node loop approach. Todini and Pilati, etc. called it the gradient method. So here's the drawing from the last video where we've got 4 pipes and 3 junctions plus a reservoir. We created the equations to solve that, and then we threw them into a spreadsheet and we just kept guessing until we found the solution. Now that approach would be kind of slow on a computer when compared to some of the other approaches available out there, like the one used in Eppanet. So if we look at the equations that we're going to try to solve here, we've got an equation for each pipe and an equation for each non-fixed head junction. So the junction equations, call those conservation of mass or continuity equations. The equations for links would be the head loss equations. So I've written these in terms of how they're set up for Eppanet. So the R would symbolize the resistance factor for each pipe, calculated from the length, the diameter, and the roughness factor that we're using, whether that be Hazen-Williams, Chesney-Manning, or Darcy-Weisbach. So essentially the equation is RQ to the N, and we're going to do Hazen-Williams, so the N would be 1.852. And then in parentheses we've got a number 1, 0, or -1 showing whether the head at the nodes are to be included in the head loss balance for the pipe. So in this case here, pipe A is from a fixed head reservoir, 100 feet, down to node 2. So we've got the head loss across there, which should equal the difference in head between the start and the end node. So the start node would be H1 and the end node would be H2. So to cancel out H3 and H4, we just have a 0 there, etc. on down through here. And the H1 is highlighted in red because it's a fixed grade node. Down here, continuity, same thing. We're using multipliers, either 1, -1, or 0, and we'll show why that is in just a minute. So around junction 2, we've got pipes A, B, and D connected. So to balance this out to equal 0, we've got flow into the junction is positive, flow out is negative. So we've got positive flow A minus flow out through B, flow through C, not a factor since it's not connected. We've got outflow through pipe D, and then we've got the outflow, the demand at junction 2, etc. So we've written that for each of these equations. Now, to set that up into a matrix solution that Eppanet uses as documented in the user's guide is A times H is equal to F. I've provided some references down in the area below the video where there's other descriptions of how this matrix equation lines up, but we can break that down into A11 or AII, AIJ, AJI, and 0, or A11, A12, A21, and 0. So where this piece of matrix comes from is we've got the equations for the pipes in the diagonal here, where we've got the derivative of the pipe equations that I just showed in these diagonals, and we can see the pipe IDs here, ABCD, ABCD, and then we've got the multipliers here of the node equations. We've got 1, -1, 0, -1. We see the same thing down here. That's where those numbers in the matrix come from. 1, -1, 0, -1. So if we remember our matrix math here, we'll remember that when we're doing matrix multiplication, we take the top row and we multiply it by this vector here, and that would equal this value here. So this vector, once we take the derivative, and the reason why we have to take the derivative is because we're using a Newton-Raphson method of converging on a solution, since we have a mixture of linear equations, which would be these equations here, and nonlinear equations, which would be these equations here. We can't do a simple matrix direct solution. We have to iterate, and we use the Newton-Raphson method of coming in on a solution, and I provide resources to understand the Newton-Raphson method. But essentially, the Newton-Raphson method is where we have, I'm not a very good artist, a nonlinear equation. You could show it by a graph like that, and we have axis q and then function of q, and so we're trying to find the roots of the function of q, which essentially would be the head loss. So we start out with a guess, and then if we come up and find the functional value, and then we draw a tangent line and find a new guess value, and we come up here and then we draw a new tangent line, and eventually we come to the root of this function. To apply the Newton-Raphson, we have to take the derivative of all the equations, and that's how we end up with these equations to come up with these coefficients. And then we're actually calculating the error in our calculation of head loss for these four equations, and then we're trying to calculate the error in the flow continuity with these equations. So what we're trying to solve for is how much do we need to change our initial guesses by to get a more accurate solution. So when we plug all those equations in, I've set this up for this network, and we've got diameter in feet, length in feet, Hayes and Williams coefficient. We can calculate a resistance factor. Eppanet also adds in, you can do minor losses for each pipe, so I've added that in as well. We start out with a K factor. Eppanet converts that with this equation to an M coefficient that can be used directly with Q squared in CFS to get the head loss due to minor losses. And here is our demand at each of the three nodes. Eppanet creates the initial guess for flow that's equivalent to 1 feet per second. So that's what these guesses are here. So to show how this works, we've got initial flow guesses, the flow at 1 foot per second. We're guessing an initial head at each junction of 0. We've calculated all of the A matrix coefficients. We've calculated F based on the equations for the error in our computations. And then to solve that, we have to multiply the inverse of the A matrix by F, and that gives us the H. So in Excel, if you're trying to do this in Excel, set up this equation. You have to highlight all of these cells then for the vector that you want to end up with, and then you type in the mmult function. So you're multiplying the inverse of the A matrix by the F matrix, and then you get this vector. So here's H. Now, what this column is we're adding this solution vector for H to our original guesses. So all I have to do here is copy and then place this over here, and we do a paste special, and we just paste those values in. And we can see how powerful the Newton-Raphson method is, because it takes one iteration to come to the exact solution.